Take it out. Ooh, who put those in there? That's incredible. In fact, it looks like there's nothing in there, doesn't it? Why don't you put those in there and we'll see if they disappear again. Ooh. Okay, do it again. Oh, look at that. So this bowl is full of those. You just can't see them. Isn't that incredible? You just put them back in there, yeah. Go on, have a go. Well, thank you very much. Now, look, before you go, I just want to ask you, do you have any idea how that works? Have you got some ideas?
Not really.
It's a tough question. It's something to do with the refractive index, isn't it?
Yeah.
Good answer. Brilliant. You are good, you. Okay, thanks very much for that. Yeah. Okay, so how did that work? Well, if light bends when you have two materials with different refractive indices, if you can match the refractive index of the balls with the water, then light won't bend. And that's exactly what we've done there. Right? We've got some balls with exactly the same refractive index as water, so light just goes straight through it. And because they're transparent, you see nothing at all. I mean, it really is effective, isn't it? But that's not going to work for an invisibility cloak, because we don't want the cloak to be transparent, because then light would just go straight through it. So we want something that bends light, but isn't transparent. And I've got an invisibility shield here. This is one of the first prototypes ever. So material scientists have made this invisibility shield, and it actually works. And let me show you how it works. So light comes in here. It gets bent round, and it goes out there. Or light comes in here. It gets bent round, and it goes out there. Right, so whichever angle light comes in, it gets bent around and it goes out the other side. So anything in the middle is invisible. You will never see it. That's incredible, isn't it? Now, how does that work? Obviously, we're manipulating the refractive index. And I want to show you a picture of it up close. So there are these tiny microscopic little interventions in the microstructure which allow us to change the refractive index, manipulate it at will to allow light to bend. Now, for this shield, it only works at microwaves, which are longer light waves than visible light. So this won't work for visible light, but it will work for microwaves. So if you were to put a cup of tea inside that little circle and put it in the microwave, it would never get hot, right? Because the microwaves would hit it, be bent round, and never get to the tea. I know, why would you put tea in a microwave? It's much better to use a kettle. That's not the point. Okay, so if we could do it for visible light, how would we do it? Well, it turns out the visible light's much shorter than microwaves, so we need much shorter microstructural features. But the principle is exactly the same, and people are working it all over the world, I can tell you. In fact, I think there might be... Sometimes I see things out the corner of my eye, and I sort of think someone's already done it, you know? No, anyway. It's just a... But this is what it would look like, isn't it? If I got an invisibility shield to work, you'd also have to solve the problem of having it flexible. But then, once you've manipulated the microstructure and got the refractive index right, you put it round you like this, and then you could just sort of say, well, imagine your teacher's coming and you haven't done the homework. You just go, I'm invisible. And you should... This is going to really change the game of hide and seek fundamentally, isn't it? Yeah. Okay, so these things are going to happen, honestly, in the next 5 to 10 years. You're going to see these things, which is incredible to think, isn't it? So far I've talked really in this lecture about us manipulating microstructures to do weird things, magic things, which are great. But nature itself does a lot of strange stuff that is just magic. And to understand that, we really need to understand what happens when we go even smaller and see how individual atoms fit together. So I've got a liquid here, and the molecules in this liquid are just milling about, doing not very much. It's transparent liquid. But if I pour it, it does something a bit odd. It turns into a solid, and it won't stop doing that. I'm even going to... And now it's just growing. Look at this. And can you see these crystals growing? Isn't that incredible? So this liquid is turning into a crystal as we speak, just like that. What are crystals? Because we hear a lot about them, and, you know, it's good to think about them a bit. So this is what we think of, isn't it, when we think of a crystal? Something with kind of these faceted sides, and it might not be as big as this. It might be a diamond ring. It might be a ruby necklace. These wonderful, translucent, transparent crystals. And they do marvelous things with light. They do marvelous things with electric fields, all sorts of crazy stuff that they do. You know, you can make lasers with them. So the crystals clearly are special materials. And what is a crystal? Well, it's an arrangement of atoms. And we saw with that liquid, it's weird because the liquid had no structure, and I poured it in, and then suddenly it got a structure. It remembered, oh, actually, we all want to be regularly arranged in a crystal. You go there, you go there, you go there. And who was telling them? Well, no one was, but they just did it. And they arranged themselves in these regular arrays. And if I show you this, you can see that crystals there are lots of different crystal types, and that's why there's such a wide range of them. And they have these remarkable, sometimes if you can line the atoms up and you get these directions where all sorts of things happen. They're fantastic things, but the one thing they don't do very well, they don't really kind of cope with, is you hitting them. They're sort of not so keen on that. Well, let's just confirm that, shall we? Crystal, hammer. Hammer meet crystal. Couldn't we make a crystal that could withstand impact and that you could bend? Wouldn't that be great? Well, they exist, and they're called metals. So look, this is what you normally think of as a metal. It's just a sort of rather grey, unremarkable, maybe brightly coloured thing. But if you look inside it, right, that's what metals are like. Okay, so if I now go back to this, right, we know what's going to happen because we've all done this to metals, but let's just reiterate that. I put the metal in there, I whack it with a hammer, and actually I'm making huge dents in it. It's not just blobs of matter are moving around, right? It's that crystals are deforming, changing shape, but everything on that impact is still crystalline. They are one of the most special crystals around, and this is how they bend. And what you're seeing here is this is a crystal, metal crystal, and these are dislocations. So they're defects in the crystal. And I'll show you one in a minute. And these things can move. In fact, they're always moving around. And you'll see in a minute there. Do you see it go? And that was under a bit of stress. So the person under the microscope was stressing the crystal, and this thing moved. And that moves one piece of the crystal from one side to the other. Here's what they look like, right? So you can see this is a crystal. It's a metal crystal structure. But you can see that there's a defect there, right? If I line it up properly, there's a defect, right? Now, under stress, this whole top of this crystal can move, and it only requires a small amount of energy to shift the whole crystal all the way along. And so that means that metal crystals can change shape in real time at the speed of sound. A crystal that you can hit, you can bend, and it moves. It reorganizes itself. So metals are great because you can mold them at high temperatures, and then you bring them to our temperature, and they're really hard and tough and fantastic materials. You can make cars out of them, airplanes, cans. The only problem with this whole scenario is that there are times when you want the crystals, the metal crystals, to survive at very high temperatures, right? Like in a jet engine. Now, jet engines are not cool places at all. I'm going to show you how kind of powerful jet engines are with this clip. So this is a 747 with 4 jet engines. Now, you'll see in a car, the engines are on, the car moves across, the power out of the back of the engine, it pushes the car, okay? That's a lot of force that's coming out of that engine. They're amazing things. They're absolutely astounding things that we've invented. And what's happening at the back here is a turbine spinning around, and they look like this, these turbine blades, and they're spinning around at really high temperatures. And these metal crystals are called superalloys. And the reason they're called superalloys is because there's only one metal that can survive these conditions, and we were so impressed with it, we called it super. I'm not joking you, that is really the why the name is called it. So these things are called superalloys, and they're an incredible structure, and they survive high temperatures, but also high stresses, because it's zooming around really fast. And I want to just remind you why zooming around, right, why rotating is such a difficult thing to cope with. And I've got a guest to help me just just show you that now. Okay, this is Sean. Give him a big round of applause. Sean has agreed to help me with this demo, haven't you?
Yes.
Because I just want to talk about why rotating something, so a blade, in the case of a turbo and jet engine, is so high stress. And first of all, we're going to do it, and then we'll talk to Sean afterwards about how high stress it was. Are you all right with this? Okay, you ready? Okay. All right? Ready? Okay, go. Run. How are your arms?